Hey everyone, thanks for coming to the talk. I'm Binghui Peng from Columbia University, and I'm very fortunate to present our paper here about training over-parameterized neural network in near linear time. This is a joint work with Jan Brandt, Zhao Song, and Omri Weinstein. Yeah, okay, first let's talk about a neural network. Yeah, the neural network is the most powerful tool in the past decades. It works so well in the practice. For example, in the ImageNet challenges, its performance keeps growing and becoming stronger over the past 10 years. And at the year of 2015, it finally beats human and achieves lower classification error than human. And its performance still keep growing over the last few years. And also in the year of 2017, the AlphaGo appears and it beats the top Go player of human. And it really surprised the world at that time. Yeah, and also for now, deep learning has attracted research from different communities over the last few years. But the problem is that while being popular, deep learning is still a mythic to many people. It has a lot of its own problems. For example, the robustness, and deep learning is also lack of explanation and over. There's still a lot of problem here. In this talk, our focus is about neural network training, and we consider the problem of speed up neural network training. Here's the outline of the talk. In the first part of the talk, I will first give a very general background introduction to the neural net. And I will also introduce the motivation behind our topic. In the second part of the talk, I will introduce a recent advance of over-parameterized neural network, and I will also describe the problem setup of this paper. And finally, I will present our result on near linear time algorithms for training over-parameterized neural network. Okay, let's start. I will first give a general introduction to the neural network and also the motivation behind our topic. Yeah, here's a few facts about neural net. The number of parameters of neural net could be extremely large. For example, there are over 10 million parameters for ResNet 18, and if the depth of the neural net becomes even larger, then this number could also become large. Yeah, the second fact is that training neural network could be very slow. For example, it takes 8 days on 8 GPUs just for training one single language model called BERT. Yeah, so based on this fact, one can see that it's really a big problem of practical neural network training. And the key question we want to ask is, can we speed up neural network training? Yeah, of course, there's no surprise that this topic has been extensively studied over past years. There are extensive efforts on this from two communities. First, from practitioners, they develop some heuristic methods, but generally there are two problems. The first problem is that this heuristic method often lack of theoretical guarantees. And the second problem is that these heuristic methods is often not scalable. To be more specific, they can only work for some specific task, but cannot generalize to all the training tasks. There has also been some efforts from the theoretical communities. For example, there are many advances on optimization literature over the past decade. But the problem is that most of this advance aim for convex optimization. But as far as people know, neural network could be non-convex and non-smooth. So there's really a gap between this advance in optimization theory and the neural network training. Yeah, this then brings the problem as follow. So how can we reason about computation time or computation cost if we are not even clear about the entire optimization landscape? That is, we are not even clear about how fast the convergence can happen and how long it takes for us to train the neural net to global optimal. Without some better understanding on this problem, we cannot talk about computation cost. But fortunately, there were some recent advance from machine learning community as well as theoretical computer science community, and they provide a firm progress on this problem and accumulated into the following result, which has been proved by separately by two groups. One is that Zhao and postdoc Sign in 2019, and the other group is Alan Zhu, Li, and Song also in 2019. So their briefly speaking, their results is as follow. So suppose the width of the neural network is sufficiently large, then one can show that stochastic gradient descent or gradient descent can provably converge to global optimal, and the training loss will converge to 0. Yeah, I will then move on to give some basic description of the neural network and the problem setup in this paper. Follow the convention of deep learning theory. We will consider one hidden layer neural network. This is a pretty simplification of the real neural net. We will use xi, yi to denote the training data, and we assume the input feature xi lies in d-dimensional, and the output label y it just comes from -1, 1. Yeah, since we just consider a two-layer neural network from the right picture, one can see the output prediction of the neural network y just equal to A transpose times y of the W times X, where X is the input feature, W is the weight matrix of the first layer, Y is the activation function, and in this paper, we take the ReLU activation function, and A is the width of the second layer. Yes, just for notation, we will use N to denote the number of training data. We will use M to denote the width of the neural network. That is the number of neurons in the first layer, and we will use D to know the input dimension. Okay, so what's overparametrized neural network? Okay, the key assumption of overparametrized neural network is that we assume the width of the neural network is much larger than the number of input data. Actually, we assume M is greater than some polynomial factor of this number of input data. And okay, after I introduced overparameter neural network, I will just leave some very brief comments on this line of work, and before I'm moving on to our results. Okay, so this overparameterized neural network provides a framework for reasoning about convergence, generalizations, and also robustness and actual. This is a really decent progress on deep learning theory. But for those who are not very familiar with this, I have to say that this is still very far from the end of the story. Okay, then I will going to present our result. The main result of this paper is that we design a near linear time training algorithms for overparametrized neural network. Okay, our result is presented in this chart. Of course, there have been a lot of study on the running time, the number of iteration, the cost of permutations about training overparametrized neural network. And this includes the first order method like gradient descent and adaptive gradient descent. Also second order method like natural gradient descent and batch natural gradient descent. But one can see from this chart, like all previous work have overall computation cost at least Mn square. So so our major contribution in this paper is we design algorithms that only have a linear dependence on Mn of cost per iteration, and the number of iteration is only log 1 or epsilon. So the overall running time of algorithm is just linear in M times N, which is essentially the best we can hope for one hidden layer neural network. Okay, I will then briefly describe the main techniques we use in our paper. Yeah, so briefly speaking, our techniques mainly falls into two parts. One is like we use approximate Newton method instead of the exact Newton method. And the second technique we used in our paper is that we do some preconditioning via sketching. Okay. So okay, the key step in Newton step, in Newton method is is to perform the following update on the weight matrix at each iteration. That's in each iteration we will update the weight matrix with the Jacobian matrix, which is further preconditioned by this the inverse of J times J transpose. Yeah, so roughly speaking here, W is the weight matrix, F is the prediction, and the J is the Jacobian matrix, and it has dimension of N by M. So what one can easily see from the above expression, the main computation cost actually comes from just the computing J times J transpose, which already takes Mn squares. Yeah, and our major techniques is to reduce this Mn square to Mn. Yeah, so our first key observation is that instead of exactly compute J times J transpose, we can actually just approximate J times J transpose and derive approximate version of this matrix, and then and we call this approximate Newton method, and we prove that actually approximate Newton method also works as long as the error is not very large. Okay, yes, so since the main cost comes from computing J times J transpose, and we can just compute approximate version of this J times J transpose. One may think of like we can approximate just using the faster JL transformation. Yeah, but actually the key problem here is that the condition number probably matters in our problem. So if we just apply fast JL to this J times J transpose, then we will incur a very huge additive dependence on N, which is bad in both theory and practice. So instead of directly use fast JL in our problem, we further divide the inner loop problem into into two steps. In the first step, we solve a regression problem, and in the second step, we use the result of regression problem to update the weight. And one can see the computation cost mainly comes from the first step, that's solving this regression problem. But fortunately, we can derive approximate solution to this regression problem by using subspace embedding to facilitate the preconditioning. And then after perform preconditioning, we can just conduct gradient descent and then find a very good approximate solution to this regression problem. And finally, this would mean the total computation cost per iteration is linear in M times N. And we also prove that the approximate Newton method has a linear convergence rate. So the total number of iterations is log 1 or epsilon, and thus the total computation cost is just linear in Mn, which is essentially the best we can hope for this two-layer neural net. And finally, I would remark that our techniques also have applications on some traditional convex optimization problem, and we can also accelerate some traditional convex optimization problems there. Okay, at the end of this talk, I will point out several future directions that that is very interesting to pursue. Okay, the first major future directions is about overparametrized neural network. And the first concrete future, so the first concrete open question in this field is that, well, it's whether we can reduce the requirement on WSM. So as one can see from the previous chart, all the results on overparametrized neural network, the ways M has some very large dependence on N. And for example, the current best result is that we need M to be greater than N to the fourth. So it's a really interesting question if we can reduce this dependence. And the second interesting future direction is to extend our algorithm to multiple layer neural network. Okay, I need to remark our algorithm have some simple extension to multi-layer neural network, and we can also achieve something like M squared times N. But it can also be achieved by some other, like maybe simple trick like tensor sketch and so on. Yeah, but anyway, the interesting question here is that can we train multi-layer overparametrized neural network in little o of M squared N? And I think this is an interesting question. Okay, the second major future direction, which I think maybe is even more interesting in the first part, is that how can we utilize randomized linear algebra in neural network training? So just in the last 2 years, there has been some dimension reduction. There have been some papers done by some practitioners that already use dimension reduction techniques to facilitate neural network training, and this technique has already been applied in practice. For example, some paper use like locality sensitive hashing, and also some fast JL transformation to reduce the computation cost in a language in the training of a language model called transformer. So here the question is, can we do more? Can we apply some more advanced of randomized linear algebra to neural network training? And the second future direction I want to say is that so can we also import linear algebra with some theoretical guarantees? So in our paper provides the first attempt to import linear algebra to neural network training with provable theoretical guarantees. But but the question is, can we do more? And maybe a more intriguing question is that can we go beyond the overparametrized neural network framework and then design some very efficient algorithms for practical neural net? Okay, that's all. Thanks.